Hello, welcome to my YouTube channel. My name is Awal Saki Mohammed. Before I proceed, I will kindly encourage you to subscribe to this channel and possibly turn on your notification button so that anytime we drop such videos, you will join us into learning to become that professional electrical person that we all desire to be. Now, today I want to talk about inspection and testing of electrical installations. First of all, before any or every electrical installation comes into being, it must first of all be designed and then installed and then inspected and tested. Now, the design is done by an electrical engineer who has the requisite knowledge and qualification and expertise, right, to be able to design the system to meet its intended purpose. Now, when the design is done, the job is given to whether a contractor or an electrician who is expected to install as per the design. Now, when the installation is completed, it must first of all be inspected and tested so that documentations can be issued for the job, right? So today we'll look at introduction, certification, electrical installation certification. We'll look at manual works, look at inspection, and then we'll look at testing. And then we'll summarize our presentation for the day. Fundamentally, there are two types of forms issued for electrical works. One is a certificate and one is a report. Now, certificates are issued for new installation works, and then reports are issued for existing electrical installations, right? Okay, so the electrical wiring regulation recognizes two types of electrical certificate. One is the electrical installation certificate, which we call ICC, and then the other is minor electrical installation works certificate, which we call Form C. Now, electrical installation certificate is intended to be issued where more significant installation has been undertaken. Examples are a complete installation for a new property or a new building, rewiring of an rewired existing installation, replacement of a consumer unit, and where addition has been made, addition of a new circuit has been made to an existing electrical installation. So basically, when the building for a new property, new electrical installation must be certified. When the building is in existence, and as the law requires certain period within the lifespan of the installation, it must be inspected and tested. And in the course of the life of the installation, when some changes like replacement of a consumer unit, distribution panel, and some key changes have been made to the installation, it must also be inspected and tested and a certificate issued. And where you make some major addition, an addition that requires an introduction of a new circuit, such changes also require the certification. And I also have what we call minor works certificate. And minor works is where an addition has been made, but that addition does not require the introduction of a new circuit, right? Such systems or such introduction are considered to be minor. An example is adding lights to an existing circuit, adding a socket outlet to a ring final circuit or a radial circuit, changing the direction or rerouting of an existing circuit, replacing of circuit breakers or replacing circuit breakers of a particular type with another type, or introducing a residual current device or RCBOs to an existing system. These are all considered to be minor works. These works do not require an introduction of a new circuit, and so it is the minor work certificate that must be issued in this regard. So then it becomes very important that the electrical professional is familiar with all the inspection and test process so that where he's supposed to issue minor work certificate, he can duly issue it. Now, inspection, section 9.1 of the electrical wiring regulation talks about why we inspect and test. So the purpose of inspection is to verify that installed equipment is A, appropriately selected and installed in accordance with the standards, right? And two, they are not defective or visibly damaged so as to limit the risk of accident. So these are the main reasons why we inspect and test. First of all, we determine that whatever has been installed meets the standard and that they are not physically or visibly damaged to cause any accident. Now we say to inspect, some part of the installation must be disconnected from the supply. And then inspection always must precede testing. You must first of all inspect before you test. And to inspect, section 9.1.1 gives us a checklist of items that we should look at during inspection. And so he said the following checklist shall, where applicable to the installation, form the basis for inspection. Look at correct connection, identification of conductors, routing of cables in safe zones or protected against mechanical damage, selection of conductors for current carrying capacity and voltage drop, and in accordance with the design of protective devices. We look at connection of single pole devices for protection or switching in phase conductors, correct connection of accessories, presence of barriers, very neat and tidy. All these things are, these are the checklist that the regulation makes provision for us to be able to go through. And in the coming video, I'll specifically touch on them item by item and showing pictorial examples of when we say correct connection. What does it mean? Basically, correct connection means that there are different types of accessories that is needed for making proper connections, right? Where you are required to use a cable lug or cable shoe, you cannot do otherwise. So there are instances where a person is supposed to use a cable lug. They find that the electrician, instead, because I don't know whether the lack of knowledge or lack of resources and all that, they are forced to wound the cable around the bolts and nuts and then tighten it. And although these things are not acceptable, and for those who even have the right accessories, sometimes they don't have the right tool. So you find that an electrician connects the cable to the cable lug, but then use a heavy object like a hammer to knock it and terminate. You need to properly crimp it. Where you use a fine stranded cable, you are supposed to use cable shoe and then use the right crimping tool to terminate it and be able to make a very firm connection. And then every cable or every terminal has a minimum size of cable or a maximum size of cable that you can carry. So when you select a bigger size of cable for a particular terminal, most of the time what happens is you are required to reduce the dimension. And when you reduce the dimension, sometimes or most times you are likely to create some high resistance around that area, which has its consequences. Okay, so these are examples of when we say correct connection. You don't terminate more than two, or unnecessary number of cables inside white terminal. All these things are not acceptable. So in wiring, you must plan your wiring well such that you avoid unnecessary loopings, right, which will result in so many cables at a particular terminal and all that. So these are basically examples of what we call correct connection. Identification of conductors. This is where color coding comes into play. This is where labeling comes into play and all that. So in the coming video, I'll touch on them one after the other, but this is to give us an idea of the items we look at during inspection. So we look at testing. Section 9.2 of the electrical wiring regulation gives us a checklist of tests that we should conduct. And it says the following checklist, where applicable to the installation, shall form basis of testing. So the lists are many, but then some of them may be applicable for a lot of the time, and some may not be applicable. So wherever you find whichever system you are testing, that is the tests that are relevant or that apply for that particular, you must make sure that you conduct them. So we say the following checklist where applicable to the installation shall form basis of testing. Say A, continuity of all protective conductors. B, continuity of ring final circuit conductors. C, insulation resistance test between live conductors and between live conductors and earth. And then we have polarity test. We have earth loop impedance test. We have earth fault loop impedance, prospective fault current, and functional testing of RCDs and RCBO. So these are the sequence of tests as provided in the electrical wiring regulation. Now, there are two, we classify these tests into two. We have what we call it the dead test, and then we have the live test. So section clause 9.2.1.1 of the electrical wiring regulation says, before supply is connected, these are the series of tests that you are required to test. You are required to conduct. And they are what we call the continuity of protective conductors, continuity of ring final circuit conductors, insulation resistance test between conductors and between conductors and earth, between live conductors and earth, polarity, earth electrode resistance test. Though these are what we call the dead test. So before a system is energized, it is mandatory that these tests are conducted. For ring, where it is not applied, you leave it, but then the radial circuit, if there's a circuit, is a socket circuit, and it's radial, that radial circuit must be duly tested. Now, where with supply connected, you are supposed to recheck polarity. You are supposed to conduct earth electrode resistance when using a loop impedance tester, and then you also expected to check what we call earth fault loop impedance, and you are also expected to check prospective fault current and functional testing of your RCDs and RCBOs. So these are the tests that you conduct. You conduct the other tests: continuity, polarity, continuity, insulation resistance, polarity. You conduct them before the system, and then earth electrode resistance. You conduct them before the system is energized. And when the system is energized, you recheck polarity, you do loop impedance, and then you check prospective fault current, and then you check RCDs for functional testing. Okay. Now, when we say continuity test, this is an example of how you conduct continuity tests on a lighting circuit. So you find that this is a socket out, this is a switch, this is the lighting point, and then this is the consumer unit. So in here, there's a CPC in the switch box running all the way to the lamp, and then it loops from there to the consumer unit. So, and when we say continuity, the interest is mostly on the circuit protective conductor. There's nothing wrong you doing your continuity to check that your wiring is properly done. But then when it comes to what you record on your test certificate, it's largely the values you get from your what we call it, circuit protective conductor. So because it is safety related, so you want to ensure that anytime there's an earth fault, there's a path for that fault current to safely dissipate into the ground, thereby causing your protective devices to trip, right? So then to test the continuity of that, there are two ways. You need what we call you can either use if it is a short circuit where your distance, which most of the time is not possible. Your leads, it's not possible for your leads for a lighting circuit to be able to touch one point to the other. So you need what we call a wonder lead or an auxiliary cable, which auxiliary cable will help you make contact to both ends of the cable. You understand? So before you do that, you make sure that you disconnect your lamp, you remove your lamp from the circuit, and then you connect one lead to, if in most cases, you hardly find people providing CPCs in their junction, in their switch boxes and all that. But then whatever it is, you must provide a CPC in your lighting circuit, right? At the light point. So you can connect one of the leads here, and then you connect your wonder lead from the earth terminal all the way to that side and test between these two, right? And with continuity, you are required to write the value. On your test form, you find we have what we call R1, R plus R2, and then we have R2. And in this case, when you do, that is where you write the R2. For lighting circuit, there's nothing like R1, R2. It's basically basically R2. And also note that the auxiliary cable that you use also has its own resistance. First of all, you must be able to establish the resistance of the wonder lead. You record it somewhere. When you have finished testing, you subtract it from the final reading. That becomes your R2. So when it comes to socket outlets, if it's a radial circuit, there are two ways of testing it. You can decide to link the live or the phase cable for the circuit you are testing to the earth bar, and then you test between live and earth at each point. The continuity is giving you an indication that there's no break in the CPC. But then this becomes the R1, R2 because you are measuring between the live and the earth. So on your test form, where you are required to write R1, R2, you write this value. But mostly you write the value for the test you conduct at the furthest point in the circuit, right? So you test here, you test here, you test here, you are doing, but then the value you write should be that of the final circuit, the socket or the circuit, the point further to the last point on the circuit, right? Okay, and then we also have this method, which is the wonder lead or wandering lead. That is, you use a cable, you connect a cable from the earth terminal, and then you connect it to one of the leads, and then you move from one point to the other, testing between the earth terminal and then the wandering lead all the way to the final point. The result, the value you write is the value you record at the furthest point, okay? So like I said, the interest is mostly on the CPC, because that is the safety, that is what provides, that is what ensures that we will be safe in the event of an earth fault. Now, you're also required to conduct continuity of ring final circuit conductor. So for ring, The rain circuit will definitely have about 6 cables, 2 CPCs, 2 live, and 2 neutral. So to test that, it becomes easy. You just connect one of the leads to the one of the cables, the outgoing, and then one to the incoming, right? And then you test, and you have you can establish the continuity of your CPC. Like I always say, there's nothing wrong you doing continuity at every point to be sure that you're on all the cables to ensure that your wiring is properly done. Okay, you can do that, but the interest is mostly on the CPC. Now, when you are finished with that, you look at insulation resistant test. With insulation resistant test, there are 2 ways of doing them. You can do an insulation resistant test on the entire installation. And to do that, you must make sure that all loads are disconnected. All switches are switched to are on the on position. If you have switches that have pilot lamp or socket outlet that have pilot lamp, you have to be careful because they will give you a misleading result. So we advise sometimes that you turn them off, right? And then you can test at the incomer of the installation. When you test at the incomer of the installation, it is giving you the insulation resistance of the entire circuit. And you find that that value will be less or be lower than what you would have achieved if you tested circuit by circuit. So let's say this one here, like this circuit was measured to be 1 megaohm. This circuit was measured to be 100 megaohm. That circuit was 100 megaohm. This one is 100 megaohm. But when they did the insulation resistance test on the entire circuit, the value that was recorded was 0.97, and that is less than even the least that was measured on one of the circuits. See, so it's basically like you connecting resistance in parallel. The total resistance will be less than the lowest resistance in the circuit. So that's basically, this way is to give you an idea of the entire electrical installation, right? But then what you record, because of the way the test forms are the values you record from individual circuits. So this diagram here, or this image here, depicts how you conduct insulation resistance tests on various circuits. So first of all, you make sure the circuit breaker is on the off position. All loads on that circuit are disconnected, all lamps removed. If they are sensitive devices like your timers, your dimmers, your regulators, you make sure they are turned off. Okay, but then switches must be on, sockets must be on, and then you test between the live or the phase cable and the neutral, and then the phase cable and the earth, right? So the value you record, we say, should not be less than 2 megaohm. That is what the LI 2008 allows. It is less than 2 megaohms. If you read other books, it says 1 megaohm. And even those books tell you any value less than 2 megaohms is an indication of a fault developing. But the LI pegs it at 2 megaohms. So take note. Now, when you are satisfied with the insulation resistance, you look at testing your earth electrode resistance. Now we say we require every earth electrode resistance to be provided with an inspection chamber. And that is to facilitate future inspection and testing. So to test it, you need an earth electrode resistance tester. And mostly they come with the 2 spikes, right? If it is the one with the 4 spikes, you can still use it to test your earth electrode resistance, but the connection may differ. So then, depending on the make and then the instructions from your manufacturer, you follow suit. But the rule is that you move about 10 times the length of the rod. You move away about 10 times the length of the rods under test. So let's say if your rod is a 4-foot rod, you go minimum distance of 40 feet. That is where you plant your current rod. And then you divide the distance into 2, and you place the potential rod. Now, when you measure, the value you get is your earth electrode resistance test. But you want to be sure that your value is actually correct. Because if you are too close to the rod that you are testing, the value may not be correct. So you want to take an average of certain reading. So you move a certain distance to the current rod, which here is saying 3 meters, and then you test. You move closer to the rod under test, 3 meters, and then you record. So you record these 2 values in addition to the first reading, and then you divide by 3. The value you get is your earth electrode resistance value. Now, the secret here is when you move closer to this rod, the 3 meter, and the value you get, there's a sharp difference between the first reading and this one. It's an indication that you are too close to the rod under test. And so to get the best value, you must move your current rod further away from that area so that you can divide, you can be outside the area of influence of that. You divide the distance into two, and then you retest. So that is when you can, when you are away from the rod and that is when you can be assured of your earth electrode resistance value. Now, if you happen to have a system which has a lot of rods connected in power, what it means is that you must have, your instrument must have the ability to, your test lead must be long enough so that you can go far away from the area of influence, from the resistant area of the rod you are testing, so you can achieve a more accurate value. Now, in summary, we looked at certification, we look at inspection, we look at testing. In the subsequent videos, I'll be touching specifically on like inspection, some of the key items. I'll show images of some wrong connections, some identification issues and all that, so that we can all learn and become the better electrical professionals that we all desire to be. Thank you very much.